So in this video, we're going to start talking about infinite series. In the last video, we talked about infinite sequences. Now we want to see what happens if I add up all of these terms in the sequence. So if you add all of these terms, you're going to get an infinite series. So like the sequences, we want to determine whether my series diverge or converge. So we're going to start by defining what an infinite series means and what it looks like. And then we're going to talk about two special types of series, which is a geometric series and a telescopic series. So let's look here. An infinite series is a sum of infinitely many terms. We can write it as this. So this is my sigma notation that we've talked about in the first chapter. So we're just adding up infinite terms. Now, the reason why an infinite series is kind of like difficult to evaluate is because I can't add up infinitely many terms. I can't add an infinite number of things. So here, instead of evaluating, like finding the value of the infinite series by adding all of these terms, what we do is we take a limit of partial sums of my series. So let's define what a partial sum means. So a partial sum of an infinite series is a finite sum of the same form of my series. So I'll take a finite number of terms. So we denote it by S of k. So here you take the same formula for your terms, but you stop at a certain number. So this partial sum is called the kth partial sum. So now, why this is important? Once we define partial sums, we're gonna form a sequence of these partial sums. So I'll have a sequence of partial sums. If this sequence converges to a real number, let's call it S, then my infinite series also converges to S. So now I can define my infinite series as the limit of the partial sum sequence, and it have the same value. So if this limit diverges, my infinite series diverges, and if this limit converges, my infinite series converges. So let's look at this example. If I have this infinite series, negative 1 half to the n minus 1, we define a partial sum by taking the same exact formula, but we stop after a certain number of terms. So let's stop after k. So let's try a few partial sums. If I'm doing S1, my S1 would be just A1. So if you plug in 1 here, you're going to get 1 half to the 0, which is 1. S2, you're adding A1, then A2. So you're going to have 1 plus 1 half, so that's 3 over 2. Then S3, you're adding A1 plus A2 plus A3. Once you simplify, you're going to get 7 over 4. Now, if we're taking the limit of S of k, we're taking the limit of this series. Once you simplify all of these terms and get like a general form, this limit would go up to 2. So my infinite series goes up to 2. We'll see how we're going to calculate this in an example that I'm going to do in a bit. So now, if you look here, I can identify the kth partial sum by my k minus 1 partial sum, because it's just sk minus 1 plus ak. From this formula, I can define my kth term as sk minus 1. So just keep that in mind for now. It's not that important. Okay, so like this sequence, I can start my infinite series with any value. It doesn't have to begin at 1. So for example, if I have this series that's starting at n equals 2, if I want my series to start my series to start at 1, because once we learn techniques of finding whether my series is convergent or divergent, usually all of these techniques must have n equals 1 to be my starting point. So let's see. If I want this series to start at n equals 1, what I do is some sort of substitution. So let's take a new variable m and make it n minus 1. So now if you do m plus 1, you'll have your n to be m plus 1. Now n starts at 2, so m is going to start at 1, because once you plug in 2 here, you're going to get 2 minus 1, which is 1. So now once you rewrite your series, you're going to have a series that starts at m equals 1 to infinity, and then instead of having n squared, you're going to have m plus 1 squared. And these variables does not matter because you can name it whatever. Okay, so let's try this example. If I have the infinite series of 1 over n plus 1, if you do the partial sums, you're going to have S1 to be 1 over 1 plus 1 times 2, so that's 1/2. S2 is going to be A1 plus A2, so you're going to get this once you simplify. Similarly, S3, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, so that's A1 plus A2 plus A3, and so on. Now, once you get the values at the end, you're going to notice a pattern. So in the numerator, I'm going 1, 2, 3, 4, 5. So in the numerator, I just have n. But in the denominator, I'm going 2, 3, 4, 5, 6. So when n was 1, the denominator was 2. When n was 2, the denominator was 3. When n was 3, the denominator was 4. So I have n plus 1 in the denominator. So now once you identify the sequence for the partial sums, you take the limit. So if I take the limit for n over n plus 1, the limit is just 1. So the sequence of partial sums converges to 1. So if it converges to 1, this means that my infinite sum converges to 1 too. So the value of my infinite sum is going to be 1. So that's it. This is how we identify infinite series with partial sums. You just try to find a sequence or a general formula for your partial sums. Once you evaluate the limit for that sequence, your infinite series is going to be equal to that value of that limit if it converges. If it diverges, then my infinite series diverges too. So the first type of series that we're going to learn is the harmonic series. The harmonic series has this formula, the summation of 1 over n. So we're just adding 1 plus 2 plus 1/2 plus 1/3 up to infinity. And this series is always divergent. The second example of or type of series that we're going to talk about is geometric series. So geometric series has this general formula. I have the infinite sum of a multiplied by r to the n minus 1. We call r the ratio, and we call a the initial term. So it kind of looks like the geometric sequence that we've talked about in section 1. Okay, so here, instead of like just putting terms, since I have a series, I'm adding up all of these terms. So a plus a times r plus a r squared, and so on. So the nice thing about the geometric series is we know a formula for when the series diverges and when the series converges. If the value for my ratio r is less than 1 and bigger than 0, this means that my series converges. And what's nice about it, I know it converges to this value always. So once you determine your r, if it's less than 1, then the series converges, and the value of the series is the initial term divided by 1 minus r. If your r is bigger than or equal to 1, then your series diverges. So let's look at this example for you. If I have the infinite series of n over 3 raised to the n plus 2. It looks like a geometric series. My only problem is it starts at n equals 0. And if you look here, the general formula for a geometric series is where n equals to 1. So here we need to do some sort of substitution to make it start at n equals 1, and then I can apply the formula directly and see whether my series converges or diverges using these conditions. So let's look here. Let's write it out. If I have n equals 0, so for the first term, you're going to plug in 0 here. So you're going to get 2 over 3 squared. Then once you plug in 1, you're going to get 2 over 3 cubed, 2 over 3 to the 4th. If you evaluate it, you're going to get 4 over 9 in each term. And so on. If you take 4 over 9 as a common factor, you're going to get 1 plus 2 over 3 plus 2 over 3 squared, and so on. So now you can think about this 4 over 9 as your A. So here, A is going to be 4 over 9, and your ratio is going to be 2 over 3. Now 2 over 3 is less than 1, so we already know that this series is going to converge. So let's write it as a series that starts at n equals 1. So I'm going to have my A, so 4 over 9, and then n over 3. Now I want to raise it to something. Since I have a 1 here, I need to get a 0 for the first term, n over 3 to the 0. But I'm plugging in 1 here, so I have to have n minus 1. Because once you plug in 1, you're going to get 2 over 3 to the 0, which is 1, which is perfect, which is what I get here, and so on. Now using the formula for the geometric series, this is going to be A, which is 4 over 9, divided by 1 minus 2 over 3. So I'm going to get 4 over 3 once you simplify. Okay, so now let's see how we're going to use a geometric series to write this fraction as an integer, or like as a fraction of integer. So let's write it out. If I have 5.2.25, I can write it as 5, 21, 21, 21, 21 up to infinity. So if you write it as fractions, this is 5 plus 21 over 100 plus 21 over 10,000, and so on. So let's simplify it as powers of 10. So this looks like a geometric series with A, your first term, and your ratio as 1 over 10 squared. So this has the sum of, using the formula of this, A over 1 minus R. Once you simplify it, you're going to get 21 over 99. So this part here is just 21 over 99. So if you want to write this decimal as a fraction, this is going to be 5 plus 21 over 99. If you simplify it, this is 172 over 33. Now, the same as the limits, series also have algebraic properties. So if I have two sequences added up inside of a series, I can split it using the sum rule. If I have a difference, I can split it too. And if I have a constant, I can take it out. But be careful. If I have a division or a multiplication inside of my series, I can't distribute it. So let's evaluate this example. Now using the properties, I know that I can split this series into two parts, and I can take the constant out. And if you notice, both of these are geometric series. So a geometric series here is with R equals 1/2, A equals 1, and here Also, a equals 1 and r equals 6 over 7. Both of these r's are less than 1, which means my series converges. I can apply the formula directly. 1 over 1 minus 1/2 minus 5 times 1 over 1 minus 6 over 7. If you simplify, you're going to get 2 minus 35, so that's negative 33. Now, the last thing that we're going to talk about today is a telescoping series. So a telescoping series is a series where a lot of terms cancel out once we're doing the partial sums. Once you cancel a lot of terms, you're going to end up with the first and the last term. So let's start with a general example. If I have a summation of bn minus bn plus 1, once you write it out, you're going to get b minus b2, b2 minus b3, and so on. So this is a telescoping series because if you can see, I can cancel a lot of the terms. Now b4 is going to cancel with something and I'm going up to infinity. So this is a telescoping series. If you do the partial sums, S1 is going to be your A1, so it's just b minus b2. S2 is going to be A1 plus A2, so b1 minus b2 plus b2 minus b3. So these cancel out, so you're going to get b1 minus b3. And similarly for S3, you're going to get b1 minus b to the 4. And if you keep going, your kth partial sum is going to be b1 minus bk plus 1. So here, we have the condition. If my bk plus 1 converges, it means my partial sum converges. So let's assume that this bk plus 1 converges to b. So my partial sum sequence is going to converge to b1, since it's a constant, b1 minus b. And we know that if a partial sum sequence converges to something, my infinite series is also going to converge to the same exact thing. Let's try this example. If I have a summation of e to the 1 over n minus e to the 1n plus 1. Let's do the partial sums. S1 is going to be e to the 1 minus e to the 1/2. S2 is going to be a1 plus a2. Once you simplify, you're going to get e minus e to the 1/3. Similarly for S3, a1 plus a2 plus a3. We're going to cancel stuff out since this is a telescoping series. So I'm going to get e minus e to the 1/4. If you keep going until the kth partial sum, you're going to get e1 minus e to the 1 over k plus 1. Because you're going to cancel a lot of terms, you're going to end up with the first and the last term only. So now if this converges, then the sequence of partial sums converges. So let's try and take the limit. So this is going to be e minus e to the 0. So this is just e to the 1, which means my partial sum sequence converges to converge to e minus 1. So the telescoping series converges to the same exact value. So that's it for section 2. You can do these problems if you want to practice, and if you go to Lumen Homework 4, you can do these problems too. If you have any questions, please let me know.